Welcome to another deep dive.
Oh, this is going to be fun.
Today, we're going to be tackling a topic that I think can be pretty daunting.
Yeah, for sure.
Efficient algorithms, right?
Right.
Yeah.
Algorithms. Everybody loves algorithms.
Well, we're not going to get lost in the theoretical jungle today.
Yeah.
We're going straight to the arena
Oh, okay.
of competitive programming,
I like that, yeah.
where these algorithms really put on a show, and our source for this deep dive is this awesome book
Nice.
on competitive programming.
Yeah.
Kind of think of it as your training manual for the coding Olympics.
That's a great analogy. Competitive programming really is about pushing those limits, right?
Yeah.
It's like, how far can you take this? How much performance can you squeeze out of code?
So picture this. You are in a coding competition.
Right.
The clock is ticking.
TikTok.
And you need to solve this tricky problem, like faster than hundreds of other brilliant minds.
Mm-hmm.
What is your secret weapon?
Algorithms. It all comes down to algorithms,
Okay.
but not just any algorithms, right? We need the most efficient ones.
Okay.
In this world, it's not enough to just find the right answer. You have to find it fast.
Right. Okay.
And that's where this concept of time complexity comes in. And we express that using big O notation,
yes.
which basically tells us how the one time of your code scales with the size of the input.
So a bigger input means more operations?
Yeah, more work to do.
Which leads to a longer runtime.
Exactly.
Okay, that makes sense.
Yeah.
But here's where it gets really interesting, right?
Yeah.
Two different algorithms can solve the same problem,
Sure.
but one might take a leisurely stroll,
Right.
and the other one sprints to the finish line.
It's all about efficiency. And the book actually illustrates this perfectly. There's this example about finding the maximum sum of a subarray.
Okay.
And a really simple brute force approach would be like, oh, let's just check every single subarray.
Yeah.
But that ends up with the time complexity of O of n cubed, meaning the runtime grows cubically as that input array grows, not a recipe for speed.
Yeah. Cubic runtime is going to hit the brakes pretty quickly.
It's going to slow you down.
So what's the secret to finding a faster solution? Like, what's the competitive programmer's trick up their sleeve?
Well, in this case, it's dynamic programming.
Okay.
Dynamic programming swoops in to save the day, and by cleverly storing and reusing intermediate results,
Okay.
it brings that complexity down to a much more manageable O of n.
Oh, wow.
So the runtime grows linearly with the input size. That's a game changer.
Big time. Okay, let's talk about sorting.
All right.
So I bet you've heard of, like, bubble sort,
Mm-hmm.
insertion sort, all that.
Yeah, the classic.
Those are kind of like the bread and butter of, like, introductory coding courses.
Right.
But in the world of competitive programming.
I don't think they'd even make it past the warm-up round.
Okay.
We need something much more powerful, right? Something like merge sort, which has a time complexity of O of n log n.
Okay, so merge sorts faster, but why?
That's a great question.
Like, what's the secret sauce that makes it so efficient?
Well, it all boils down to a really clever divide and conquer strategy.
Okay.
So imagine you take your array and you just split it in half, and then you split those halves in half, and you keep doing that until you have these tiny little subarrays that are really easy to sort. And then you merge those subarrays back together in sorted order.
So even though it's recursive,
Right.
the process of repeatedly dividing the array in half is what leads to that logarithmic efficiency.
Exactly. That's the key to merge sort speed.
Okay, so is O of n log n, is that like the best we can do
That's a great question.
when it comes to sorting algorithms? Like, is there some ultimate speed limit?
Yeah, that's a really fundamental question. It turns out that for comparison-based sorting, O of n log n is actually a barrier. You can't do any better than that.
Okay.
The book actually goes into the mathematical proof of that if you're curious.
I love that there's always something more to discover. Okay,
Always more.
let's talk about another algorithm that's a staple in, I think, every programmer's toolkit.
Okay.
Binary search.
Yeah, binary search.
You're probably familiar with its ability to find an element in a sorted array in of log n time,
Yeah,
right?
absolutely. It's a classic.
Yeah, but in competitive programming, binary search actually takes on
It gets even cooler.
an even more powerful role.
Yeah,
It's not just about finding elements.
right.
It's about finding the smallest solution that satisfies
Oh,
a certain condition.
interesting.
Yeah. So walk me through like how that actually plays out in code.
All right, so imagine you're trying to find the smallest value k
Yeah.
that meets some requirement. So you can write a function, like, call it OK,
Right.
which checks if a given value x is a valid solution.
Okay.
And then binary search swoops in and says, all right, I'm going to find the exact point where that OK function goes from false to true. And that point, boom, that's your smallest valid solution K. It's a really powerful technique.
So it's like binary search isn't just searching for a needle in a haystack anymore.
It's more than that.
It's figuring out the boundaries.
The threshold.
Where things change, yeah.
Yeah.
Okay, so I hear this book is packed with C++ plus specific tips and tricks that can make even seasoned programmers raise an eyebrow.
Oh, yeah. There's some good stuff in there.
Let's talk about data structures first. So
Yeah.
you've probably worked with arrays a lot.
Arrays, yeah, they're everywhere.
But in competitive programming, sets and maps can be real game changers.
Absolutely. Sets and maps, they bring a lot to the table.
Okay.
Sets, they make sure all their elements are unique. So you can think of them as like the ultimate deduplicator.
Right. Because arrays are essentially just a sequence of elements.
Yeah.
While sets and maps offer more structure and specialized functionality.
Okay, yeah, exactly. And then maps, they let you associate like any data type with a key, which gives you a lot more flexibility than just using arrays.
Right, okay, yeah. Now, this book emphasizes the importance of shortening code in competitive programming.
Oh, yeah.
I mean, time is of the essence.
Time is precious. Every keystroke counts.
What are some techniques it recommends for writing concise, lightning-fast code?
One powerful technique is using typedefs to just create shorter aliases for commonly used data types.
Okay.
So instead of writing out vector int every single time,
Yeah.
you could just have a typedef that shortens it to vi,
Okay.
makes your code more concise and easier to read.
Right.
And then there's macros,
Okay.
which are basically predefined code snippets
Ah, okay.
that you can use throughout your program. They're great for getting rid of repetitive code blocks.
Macros are like those handy keyboard shortcuts,
Yeah, exactly.
but for code.
Yeah,
Can
exactly.
you give me an example of how a macro could be used in competitive programming?
Absolutely. Imagine you're working with a for loop and you use it all the time.
Yeah, for sure.
You could define a macro, like, and I'll just say it out loud, define RDPI AB for int I equals A, I less than or equal to B, I plus plus.
Okay, so then instead of writing out that whole
Yes.
for loop every time,
You just use REP.
use REP.
I want n to loop from 1 to n.
Oh, that's so helpful,
That's-
especially when you're racing against the clock.
It saves you time.
Saves you time. Okay, now let's tackle a big one,
Oh, boy.
dynamic programming.
All right.
I'll admit, this one has always felt a bit like a puzzle box to me,
Yeah.
but I'm ready to crack it open.
It is a bit of a puzzle box, but I think this book explains it in a way that finally clicked for me.
Okay.
The core idea is to solve problems by breaking them down into these smaller, overlapping subproblems.
Okay.
And the genius part is you store the solutions to these subproblems as you go, so you don't have to waste time recomputing them later.
So you might be wondering, like, how does storing solutions actually save us time?
That's a good question.
Well, imagine you have a problem with, like, many overlapping subcalculations. Dynamic programming lets you avoid
Redundant.
doing the same work over and over again. How about we use a classic example from the book to illustrate this, the coin problem.
Ah, yes, the coin problem, a classic.
So imagine you have a set of coins with different values, and you need to figure out the minimum number of coins needed to make a specific sum.
Right.
Let's say our target sum is 10,
Okay, 10.
and we have coins with values of 1, 2, and 5.
Okay.
How would we approach this with dynamic programming?
So the recursive approach would be like, okay, let's try each coin, subtract its value from the target sum, and then solve for the remaining sum.
Okay.
But here's the key.
Okay.
We store the solution for each sum we encounter along the way, so we don't have to recalculate it later. This technique, it's called memoization,
Okay.
and it's like the heart of dynamic programming.
So we're building up a table of solutions as we go.
Yeah, you got it.
And so we might find, like, the minimum number of coins to make 5 is 2. Let's say, like, 1 coin of value 2 and 1 coin of value 3. And then if we later need to make a sum of 8, we don't have to start from scratch. We can just look up our stored solution for 5 and build from there.
Exactly. That's the power of it. You're reusing those previous results.
I'm clever.
It's all about being smart.
Wow, this competitive programming world.
The wild
It's
word.
full of, like, these ingenious tricks.
Oh, yeah.
And we're just scratching the surface.
We're just getting started.
What other secrets does this book have in store for us? I'm ready for more.
Oh, there's plenty more where that came from. Buckle up. Yeah, It really is remarkable, like, how many clever techniques they've got up their sleeves.
Right.
Like, this book is a treasure chest
Oh, yeah.
of algorithmic ingenuity, and it really pushes you to think
It
differently
really does.
about, like, code optimization.
It's like, those cooking competition shows where they have to, like, make a gourmet meal with, like, limited ingredients
Yeah.
and time. It's like
It's like, yeah, under pressure.
competitive programmers are like, the bestest of the coding world.
Yeah, they're whipping up those elegant solutions under pressure.
Yes, exactly.
And speaking of pushing the limits, this book kind of goes into this world of advanced algorithms.
Ooh, advanced algorithm.
The kind that really take optimization to a whole new level.
Okay, so what kind of problems do they tackle? Like, what makes them so special?
So they're designed to kind of solve these more complex, specialized problems that often pop up in competitive programming.
Okay.
Take amortized analysis, for example.
Right.
It's basically a way of understanding the average cost of a sequence of operations,
Okay.
even if some of those operations might seem expensive on their own.
So it's like budgeting for your expenses over a year.
Yeah.
You might have some big bills here and there, but you average it out and you're still within budget.
Exactly.
But how do you actually calculate that amortized cost? Like, is there a formula or is it more of a conceptual tool?
It's a little bit of both. There are some mathematical techniques for analyzing it, but it also involves like a conceptual understanding of how the algorithm behaves over time.
Okay.
A great example from the book is this thing called the two pointers method.
Oh.
So imagine you have this array of numbers and you want to find the nearest smaller element that appears before each number.
Okay, I can see how that could be useful.
Yeah, right.
It's like looking back in time to find the most recent dip in like a stock price or something.
Exactly.
How does the two pointers method work its magic?
So basically you have 2 pointers, one to kind of scan through the array,
Okay.
and the other one to keep track of potential smaller elements.
Okay.
And as you move the first pointer forward, you got to adjust the second pointer to maintain a specific property,
Got it.
like maybe keeping track of the smallest element you've seen so far.
Right.
And some operations might involve moving that second pointer a lot, making them seem costly
Yeah, but then if you average it out over all the operations,
over the long haul.
it becomes more efficient.
Yeah, you're taking the long view.
Okay, so what other advanced algorithms does the book explore?
Oh, there's tons.
Okay.
Well, there's another cool category called square root algorithms.
Okay.
Remember we talked about those with the range query example earlier?
Yeah. That's the
Dividing the data.
dividing the data into blocks of size root n.
Exactly, like organizing a library into sections
Yeah.
to make searching faster.
I like that analogy.
And that square root block size often provides like a sweet spot for balancing the cost of processing the blocks
Right.
with the cost of checking individual elements within those blocks.
Okay, so I'm definitely seeing a pattern here.
The square root.
The square root seems to be a recurring theme in these advanced algorithms.
It pops up everywhere.
Are there any other tricks that kind of leverage this magical number?
Oh, yeah, absolutely.
Okay.
The book shows how these square root algorithms can be applied to all sorts of problems, not just range queries. They're even helpful for finding those nearest smaller elements we were just talking about. It's like a super versatile tool.
Powerful.
Yeah.
Now, you mentioned sweepline algorithms earlier.
Yeah.
They sound kind of like sci-fi, right?
They're so cool, they're so elegant, and they're very visual.
Okay.
So imagine you have this vertical line sweeping across a plane from left to right,
Okay.
like a radar scanning a landscape.
Okay, I'm picturing it.
And as that line moves, it encounters events, like points or line segments.
Like watching a laser scanner, yeah.
Exactly. And the key is that by processing these events in the order they're encountered by that sweep line, you can solve problems that would be much harder to tackle otherwise. A classic example, finding the closest pair of points.
Wait, you can use sweep lines to find the closest pair of points.
Oh, yeah.
How does that even work? It sounds like magic.
It's more like cleverness
Okay.
and efficiency.
Right?
So you start by sorting the points by their x-coordinate. So that sweep line encounters them in order. As that line moves, you're keeping track of the points that are within a certain distance to its left.
Right.
And when the line hits a new point, you only compare it to the points within that distance.
Okay.
Because the points farther left, they can't be the closest.
So you're basically narrowing down the search space as you sweep across the plane.
Exactly.
That's a huge time saver.
It is. It transforms what could be like an O of n squared problem, where you're comparing every pair of points into a much more efficient O of n log n solution.
Wow.
It's a prime example of how a simple visual concept can lead to some really powerful optimization.
Yeah, I'm starting to understand why these advanced algorithms are so fascinating.
Fun stuff.
It's about finding these elegant shortcuts,
Right.
these patterns that can shave off that precious time
Yeah,
and make your code really shine.
exactly.
Well, we've covered a lot of ground already.
We've been on a journey.
From the basics of time complexity to these mind-bending advanced algorithms.
It's a lot to take in.
But there's one topic I'm particularly curious about that the book kind of touches on. Dynamic programming.
Oh, yeah.
It sounds really powerful,
It is powerful.
but also a bit mysterious.
It's like a secret weapon.
What's the secret behind this technique?
So dynamic programming, it's like one of the most important tools in a competitive programmer's arsenal.
Okay.
And the basic idea is to solve a problem by breaking it down into those smaller, overlapping subproblems,
Okay.
and then storing the solutions to those subproblems so you don't have to keep recalculating them.
Right. So you mentioned this earlier with the coin problem, right?
Yeah, the coin problem, classic example.
Can you give me another example of how dynamic programming is used in competitive programming?
Oh, absolutely.
Okay.
Let's look at the problem of finding the longest common subsequence of two strings.
Longest common subsequence. Okay.
Yeah, so imagine you have two strings, like banana and Atlanta. And the longest common subsequence is the longest sequence of characters that appear in both strings, in the same order, but not necessarily consecutively.
Okay.
So for banana and Atlanta, the longest common subsequence would be ajanta.
Okay, so it's like finding this hidden pattern that connects those two words.
Exactly, it's like pattern matching.
Okay.
Now, the brute force way to find this would be to compare all possible subsequences of the two strings,
Right.
which would be a computational nightmare.
Yeah.
But with dynamic programming, you can build this table that stores the lengths of the longest common subsequences for all prefixes of the two strings.
So it's kind of like we're using a table to keep track of intermediate results like we did with the coin problem.
It's a similar idea.
But how does this table actually help you find the longest common subsequence?
So each entry in the table represents the solution for like a smaller subproblem.
Okay.
And you kind of fill in the table step by step, using the solutions for the smaller subproblems to calculate the solution for the next larger subproblem.
So you're building up a solution from the ground up, basically.
Yeah, you're building it up.
Reusing previous results to avoid unnecessary calculations.
Like building a pyramid, you start from the base and you work your way up.
I like that. Dynamic programming is like a master builder
Yeah.
carefully assembling this complex structure.
Yeah, piece by piece.
Piece by piece, that's a brilliant technique.
It's powerful.
Now let's shift gears a bit and talk about another key aspect of competitive programming,
Okay.
mastering the art of writing efficient C++ code.
Right, because it's not enough to just know the algorithms.
Right.
You got to implement them well.
Yeah, so I'm eager to hear what kind of C++ wizardry this book has to offer.
There's some good stuff in there.
Okay.
Well, it starts with the basics, like using typedefs to create shorter names for commonly used data types.
Okay.
This makes your code more concise,
Right.
easier to read and write, which is crucial when you're under pressure.
Type deaths are like those handy nicknames you give your friends.
Yeah, exactly.
Shorter, easier to remember.
Everyone knows who you're talking about.
What other C++ tricks does the book have up its sleeve?
Well, it goes into some pretty cool techniques, like using macros to avoid writing the same code over and over again.
Ah, macros, those little time savers.
They're lifesavers.
It's all about maximizing efficiency, isn't it?
Efficiency is key.
And it even delves into more advanced techniques, like bit manipulation, which allows you to, like, work with individual bits within integers.
It's getting down to the nitty-gritty.
Bit manipulation. That sounds like something only hardcore hackers would use.
It might sound low level, but it's incredibly powerful for certain types of problems.
So how is it actually used in competitive programming?
One common use is for representing sets.
Okay.
So imagine you need to keep track of a set of numbers.
Okay.
Instead of using like a traditional set data structure,
Right.
you can actually represent the set as a bit mask, where each bit represents a number.
So if you have a set of numbers from 1 to 10, you could use a 10-bit integer, where each bit indicates whether the corresponding number is in the set or not.
Exactly, you got it.
That's a pretty clever way to save space, but how do you actually work with these bit masks?
That's where bitwise operators come in.
Okay.
You can use operators like AND, RR, XOR, and bit shifts to perform operations like adding elements, removing elements, or checking for membership.
Okay.
And because these operations work directly on the underlying binary representation of integers, they're super fast.
So it's like speaking the computer's language directly,
Yeah, you're getting down to the hardware level.
bypassing all those layers of abstraction.
You're cutting out the middleman.
Bit manipulation is like this secret language that unlocks a whole new level of performance optimization.
It's a powerful tool.
What about number theory? How does that play a role in the world of competitive programming?
So number theory, it's this branch of mathematics that focuses on the properties of integers. It might seem abstract, but it actually has tons of applications in competitive programming. A lot of problems involve concepts like prime numbers, divisibility, modular arithmetic, all this number theory stuff.
Okay, I can see how understanding the behavior of numbers would be helpful when you're dealing with algorithms that process numerical data.
Absolutely.
Can you give me an example of how number theory might be applied in a competitive programming problem?
A classic example is using modular arithmetic to handle calculations with very large integers.
Okay.
So modular arithmetic, it's this system where numbers kind of rack around after reaching a certain value called the modulus.
Okay.
Think of it like a clock. After 12 o'clock, the hours start over at 1.
Right.
So instead of dealing with these huge numbers that could overflow the computer's memory,
Yeah.
you can use modular arithmetic to kind of reduce them to manageable sizes
Right.
while still preserving the essential mathematical relationships.
So it's like a mathematical shortcut.
Exactly. And that's just one example of how number theory can be applied.
Wow.
There's a whole world of mathematical tools and techniques out there.
That's incredible.
Yeah, it's really amazing how competitive programming makes you rethink like how you write code.
Right. It's like you're not just building something that works. It's like you're sculpting it for like optimal performance.
Yeah, it's the difference between building a house and designing a high-performance race car.
Right.
Every component matters when you're going for speed.
Exactly. And speaking of components, let's talk about data structures.
Okay?
So we all learn about arrays and lists, all the usual suspects.
Right.
But this book highlights some data structures that might not be on everyone's radar,
Okay.
but are incredibly useful in competitive programming.
Interesting.
You talk about sets and maps, right?
Sets and maps, yeah, they're both part of the C++ standard template library,
Okay.
and they offer some really cool features that can make your code a lot cleaner and a lot faster.
Okay, I'm ready for a refresher. What makes sets and maps so special, like compared to arrays?
All right, so think of sets as arrays that automatically enforce uniqueness.
Okay.
So you can add elements to a set, but it's only going to keep one copy of each element.
Okay.
No duplicates allowed.
Got it.
This is super useful in scenarios where you need to keep track of distinct items.
So if you're dealing with a problem where duplicates don't matter or even like problematic,
Yeah.
a set is your go-to data structure.
Sets are your friend.
What about maps? How do they fit into the picture?
So maps take things a step further. They let you associate any data type with a key.
Okay.
It's like a dictionary where you look up a word, the key, and you find its definition,
Right.
the value. But unlike arrays, the keys in a map, they don't have to be integers.
Oh.
They can be strings, objects, whatever you need.
So maps offer a lot more flexibility than arrays.
Oh, yeah. Way more flexible.
You can use them to represent relationships between different types of data in a really elegant way.
Absolutely. It's all about elegance.
Exactly. Okay. I'm starting to appreciate the versatility of sets and maps now.
They're powerful tools.
The book mentions some pretty advanced stuff too, like bit manipulation and number theory.
Right.
Are these really essential for competitive programming, or are they more like specialized tools for these like niche problems?
Well, they might sound intimidating, but they're actually really powerful tools in the right hands.
Okay.
Bit manipulation especially can make your code crazy fast for certain types of problems.
Okay.
It's all about working directly with the individual bits that represent data in a computer.
Bit manipulation sounds like something straight out of the Matrix.
It's a little bit like that.
How does it actually work in practice? Can you give me like a concrete example?
Sure. So remember how we talked about representing sets using bit masks?
Yeah.
Let's say you have a set of numbers from 1 to 10.
Okay.
You can represent this set as a 10-bit integer, where each bit corresponds to a number.
Right.
If a bit is set to 1, it means the corresponding number is in the set.
Okay.
If it's 0, it's not.
So it's like a binary code where each bit acts as a flag
Ex-
for a specific element.
You got it.
But how do you actually manipulate these bit masks to do useful things,
Hmm.
like adding or removing elements?
That's where bitwise operators come in.
Oh,
You have operators like AND or XOR and NOT,
right.
which let you perform these logical operations on individual bits.
Okay.
And because these operations happen at the hardware level, they're super
Right.
fast.
It's like bypassing the software and talking directly to the silicon.
Yeah, you're cutting out the middleman.
Can you give me an example of how a bitwise operator might be used to manipulate a set represented as a bit mask?
Sure. So let's say you want to add the number 5 to our set,
Okay.
represented by that 10-bit bit mask.
Okay.
You would use the OR operator to set the 5th bit. Remember, we're counting from 0
Right.
to 1.
Okay.
Similarly, to remove an element, you would use the AND operator to set the corresponding bit to 0.
So it's a really elegant and efficient way to work with sets.
It is. It's very elegant.
Manipulation is like this secret language that unlocks a whole new level of performance optimization.
It's a secret weapon.
Okay, what about number theory? How does that play a role in the world of competitive programming?
So number theory is this branch of mathematics that focuses on the properties of integers.
Okay.
It might seem abstract, but it has a surprising number of applications in competitive programming.
Okay.
Many problems involve concepts like prime numbers, divisibility, modular arithmetic,
Right.
all sorts of number theoretic concepts.
Okay, so I can see how understanding the behavior of numbers would be helpful when you're dealing with algorithms that process numerical data.
For sure.
Can you give me an example of how number theory might be applied in a competitive programming problem?
Yeah, a classic example is using modular arithmetic to handle calculations with very large integers.
Okay.
Modular arithmetic is a system where numbers wrap around after reaching a certain value, called the modulus.
Okay.
Think of it like a clock. After 12 o'clock, the hours start over at 1.
Right.
So instead of dealing with these huge numbers that might overflow the computer's memory, you can use modular arithmetic to reduce them to manageable sizes while still preserving those essential mathematical relationships.
So it's like a mathematical shortcut.
It is. It's a shortcut.
This has been an incredible deep dive
It has been fun.
into the world of efficient algorithms and competitive programming.
We covered a lot,
We've covered so much ground.
from basic time complexity to sweep line algorithms,
Bit manipulation.
number theory.
I feel like I've gained a whole new appreciation for the power of algorithms.
It is powerful stuff.
And the creativity involved in crafting these optimized solutions.
Oh, absolutely.
This deep dive has definitely sparked my curiosity.
Good. I'm glad.
I might even try my hand at some of these competitive programming challenges.
You should. You should.
Who knows, maybe I have like a hidden talent for algorithmic optimization.
You never know until you try.
Well, thank you so much for joining me on this incredible journey. It's been a real eye-opener.
It's been a pleasure.
And for our listeners out there, keep those brains buzzing and those algorithms humming. We'll see you next time for another deep dive into the world of knowledge and discovery.